Got some more Chapter 7 problems that will turn in this Friday. And then we're cut into some Chapter 8 stuff. I'm going to streamline all this Chapter 8 stuff. So a lot of times I go off topic. I start bringing in a bunch of comparisons to ways other people do things. I think what I'll do is I'll just leave Bayesian testing out. I will talk about it on the final day of class. So that's not this Wednesday, but next Wednesday. Is that right? May 1st. So I'll tell you what Bayesians do, I'll tell you where the divide is there, and I won't test you on Bayesian testing. So, sound good? So I'm just going to streamline it so the problems kind of look like what they just do in the book, and just prepare you for the exam. I think that'll be good enough for me. And then I'll tell you a little bit about controversies. I'll sprinkle that in, and then I'll make a bigger deal about it on next Wednesday. Cool. Okay. Let's just pick up about where we were last time. We were studying the likelihood ratio test. We had done a normal example. If you didn't catch the very end of that, we needed the sigma over root n in that example, and we tried to fill that in right at the end. We might not have seen all of it, so if you do sit in the back and you jump up right at the end, it'll take out the camera. So, and we won't be able to see that stuff. I don't know, it's kind of blurry on the screen. So just be aware of that. If you're standing right in front of the camera, take a step to the left or to the right. So, thanks. Let's just pick up with a different example real quick and do a likelihood ratio test and do something simple, similar to what we did last time. But we'll recover that example with normality in a second. I'll show you more about what people do with that thresholding technique. So, here's an example. This one is also in the book. Let's say xi's come from f of x, given theta, and this model is going to be e to the minus x minus theta, where x is greater or equal to theta, and this is 0 otherwise, so x is less than theta. Let's just draw a picture of this. So x is greater than theta, so let's draw theta right here. We know what this function looks like. This is just an exponential distribution. This is not asymptoting into this. This is cutting through this. And then we're erasing that part. So that's what this distribution looks like. Does anybody have a name for this distribution? Truncated something. Yeah, good name. So, shifted exponential. I guess they're all truncated. So, at 0 usually is the normal truncation point. So, I would call it the shifted exponential. But yeah, it's truncated here at theta. I think that's a good name too. So, I kind of like talking about shift because it makes me think of something a little bit differently. Just real quickly, what's the sufficient statistic for theta? Can you just glance at it and tell me? Very good. So it is. It's the thing that's bunching against theta. So if you were thinking that the sum of the xi's might be the sufficient statistic, you're probably thinking of a problem like this. You know, lambda is over in the front, and then I would rescale everything by lambda here. So the typical exponential thing, then the sum of the xi's would be sufficient for that rate parameter. So, and if I had the lambda in there and the theta, then the min would tell me about theta, and the sum of the xi's would tell me about that rate or scale parameter, depending on how I parameterized it. It would either be x bar or 1 over x bar. And I can make problems tricky by making it 1 over x bar as the test statistic or something like that. That's kind of harder to work with because then I have to find the distribution of 1 over x bar. So, 1 over x bar is not too hard to think about. If you're sitting at home and we had our books next to us, it would probably be something like an inverse gamma distribution that it would follow. Some of the xi's would follow a gamma distribution. So all things just to be thinking about when you see problems, you can kind of generalize them and make them a little bit more complicated. Okay, I like these problems where they have the min in there, so it kind of makes us think about what we studied in chapter 5. We might need probability distributions of mins, and that's where we're going with that, this sort of thing. We won't do the full-blown example, we'll just start setting it up. So we want the likelihood ratio test statistic. Just keep in mind we collect data over here, more points over here because it's denser over here, and this is the min. So we could write down a likelihood function. And this would be proportional to product I goes from 1 to n, e to the minus xi minus theta, right here. We'd have to be careful and also plug in this constraint right here. So to get everything, so all of the xi's are greater than theta. And then we can kind of simplify this. We can simplify this part. This is e to the minus some of the xi's. I'm going to say plus n theta, so just be careful where the brace ends. This used to drive me crazy in college, where it's like, where's the braces? I want to know where that negative sign is being multiplied by. So anyway, this negative sign is just with this part. And then I can drop this part down too and simplify that form. And this would just be delta function. The minimum is greater than theta if all of the xi's are greater than theta. So it's something very similar to what we did months ago. So that's my likelihood function. The likelihood ratio test statistic. This is just the maximum theta element of the null space, so I probably have to set up a test in a second to even talk about what this space is. I haven't written it on the board yet. We'll do that in a moment. So let's put this all in the numerator. Likelihood, same exact likelihood function over here. And the way the book introduces this is to divide by the maximum likelihood. Just keep in mind, they do shift this on you eventually to say theta's in the alternative space in the denominator, and that will not change very much. It might change a little bit of the arithmetic, but it's basically the same test. If I just divide by the maximum likelihood test statistic, that bounds the statistics between 0 and 1. If I divide it by the maximum in the alternative space, then it would be some positive thing, but it could be not bounded by 1. So it's kind of nice to have things set up by 1, to be bounded by 1, so we know it is big. So saying that, I can think about it exactly the same way on a 0 to infinity scale. I just don't have as good of an intuition about that. The book does switch this eventually, without telling you. So I'm telling you. So when we get to David and Pearson, the condition that they're studying is the max likelihood ratio test statistic in this other formulation. So maximizing over the null, dividing by maximizing over the alternative. So we'll talk about that when we get there. And so we come up with this, so we just need to work this thing out. There's a couple possibilities here. Let's just draw the likelihood function. So the likelihood function, this thing, looks like this. Function of theta. And we can kind of just stare at where the theta is in here. So this is positive. So as theta is increasing, this whole function is increasing. So it looks something like this. Is what that function looks like. Depending on what n is the steepness of this function, how fast it goes up. But I've got some restrictions in here. And so we're bounded by x1 on all of this. So it's where does this thing truncate? It's x1 is the truncation point. So we just have to think about this a little bit. The pictures look similar, but they're flipped around. Because we're flipping around the whole function and thinking about it a little bit differently. It's a function of theta instead of a function of x. So this is a function of x here, and this one's a function of theta. So we can get rid of that, and the likelihood function just truncates right there. If you want to think about that, you can put it in like that. So that's the likelihood function. So we just need to think about a few things. Let me give us a test. So let's do I'll save myself a little bit of room here. H naught, I think this is what they did as well. Maybe it's less than theta naught. This is the one that makes sense to me. Theta is greater than theta naught. So let's just write this thing down. Let's stare at our picture. This is what I like to do. I like to envision likelihood functions. It's my favorite thing in the world to do is just sit around and think about what does the likelihood look like, because that gives me most of the information. So, okay, I don't do that for fun all the time, but I think it's an important exercise. If I were going to go back and redraft all of statistics and start us out in Stat 101, what I would be doing is just having people draw likelihood functions. That'd be it. Over and over and over again. Where do you think the truth is? Somewhere around here, and then build up that concept and turn it into something more concise by adding in some constraints. So likelihood functions are the name of the game in inference. If you're not using likelihood functions and you do really well, you got lucky. There's our likelihood function right here. I can think about if theta naught is over here. So if theta naught was over in this region right here, then I know that the maximum would occur at that point right here, because the likelihood is actually coming down right here. So the maximum likelihood estimator is this point. That's pretty obvious from the picture. And so if theta naught was greater than x1, then this likelihood ratio test statistic would be 1. Let's write that down. So lambda x will be 1 if theta naught is greater or equal to x1. If theta naught was over here, on the left-hand side of x1, then the maximum in the null space, so this would be our null space right here, all the way up to that point. So this is our null space, and this is our alternative space. I'll call it HA. A lot of times I use alpha, sometimes I use H1, I mean the exact same thing. So this case is a little bit more interesting. So theta naught's over here, the maximum in the null space occurs on that boundary. So that's an important thing, is that the maximum occurs on the boundary. That's where you have the most power to detect this, is because this is going up there. We'll talk about that when we get to power functions in a moment. So this is going to be e to the minus sum of the xi's plus n theta naught is that maximum value, where theta naught is less than x1. And then I'm going to divide by the maximum likelihood ratio, or the maximum likelihood. So this is going to be e to the minus sum of the xi's plus n x1. So that's my likelihood ratio test statistic. So what do we do with this? This is all very mechanical in these cases. I have this condition that I'm going to set up, and I'm going to truncate it at some value right here. And this is just going to determine ultimately some probability on rejecting everything. Keep in mind everything is defined in a probability model, so I can calibrate this to a probability. I'll show you an example like that a little bit later. This is just some number between 0 and 1. So I'm going to reject if this is true. And that's going to determine my trade-off in making different types of errors concerning the decisions. Either the null is true or the alternative is true, and there's two different types of errors. And we'll address those errors in a minute. So there's two things you can do, but I come up with some decision as to whether or not I want to reject it. This makes sense because if this is small compared to that, I probably want to reject it. So i.e. if the likelihood is small in the null vicinity compared to the likelihood period, then probably we want to reject the null. So I think that all makes sense. So I don't see any arguments yet. All this stuff makes conceptual sense to me. It makes mathematical sense. And in fact, I don't have a problem with this example as well. So whoever plays around with this example and does things reasonably, will probably agree with their inference, so long as they're using x1 the minimum test statistic and doing the right thing. If I saw that they were using some other test statistic, then I'd probably think, oh, you're totally beat it. Okay, so again, everything makes sense here. So we're going to truncate this part. That's probably the more interesting thing to look at. So if this is true right here, if somebody came up with a hypothesis that theta naught was something that was bigger than x1, then I would just say, yeah, you can't reject that. So that's unrejectable. But if theta naught is less than x1, then maybe you have an opportunity to reject it. So this thing is just going to look like this. E to the minus, I'll just do some simplifications. Let's just call this n theta naught minus x1. Put that in braces. So this is simplified, so the sum of the xi's cancels out of all of this. You'll notice that this thing only depends on the sufficient statistic. We could have proven that. The book does prove that. It says the maximum likelihood ratio test statistic only depends on the sufficient statistic. Proof, factorization theorem. So just change out this likelihood function for that factor, for those factors that we studied in the factorization theorem, and the hx stuff will cancel in here, and you'll just be left with that g function that depends on the sufficient statistic. We see that in this example. So the sum of the xi's canceled out. If there had been a rate parameter, that wouldn't have canceled out, because I'd be studying that parameter as well. So I'm going to bound this by some number c, and then I'm just going to do some simplification. Get rid of this. So this is equivalent to, I'll take the log of c, that's some negative number, I'll divide by n. I'm left with theta naught minus x1 over on the left-hand side right now. So I'm going to flip this thing around. Let me do this. I'm going to say minus x1 is less than or equal to this minus theta naught. So I think that's correct. So always the biggest struggle doing algebra at 9 o'clock in the morning. I think that's correct. This looks a little peculiar, so let's just get rid of that, flip this thing around, and do that. And that's probably an impolite way to write it. That would definitely give me some problems if I were trying to extend this problem. So let's just rewrite this. x1 is going to be greater or equal to theta naught minus log c divided by 10. So this defines some rejection region. I'm going to reject if this is true. So reject if. What we haven't talked about is how to pick c in all of this. But we just have some idea, we pick some threshold, we want to understand what the correct balance is in that threshold. But we kind of understand that our answer depends on that threshold, and that's going to determine kind of which type of error we make. So if I ended up picking C to be 1, for instance, then I'm probably not going to reject very often. So I'm never going to reject on that. Or sorry, I'm going to reject every single time. I'm always going to reject. So if the null is true, I have a huge error that I'm going to incur. So, but my other type of error is 0. So that's the trade-off that we might expect. So that's our reject if statement. So this is defining a rejection region. So I'll just call this rejection region. And the rejection region is a function of your sufficient statistic. And it can always be compressed in your minimal sufficient statistic. I can think about rejection regions in terms of a whole n-dimensional data space, but ultimately it's only being defined through the minimum. So I can think of all this huge space, n-dimensional space, what the rejection region is, or I can think about this one-dimensional space and think about what the rejection region is. I would rather think about this one. So that's just another kudos to min sufficiency. Using it simplifies our life a little bit. Okay. let me tell you about power functions. So here's a definition. A power function is the probability of rejection. Probability of being in the rejection region. I'm going to give the rejection region a name, R. Here's an example of a rejection region for a problem. So I can encode that as R and say that it's some rule, and I've got some explicit rule for rejecting. So we'll just generically call whatever that rule is for any problem R. So it's basically just a thresholding on the likelihood ratio test statistic is typically what we use for that. So this is probability of X, element of R, given theta. So this is dependent on the parameter itself. And the parameter could either be in the null space or in the alternative space. Very typically, people think of this function as only being defined in the alternative space, but I can also define it in the null space. So if you were taking a Stat 101 type class, they would probably talk about power in the alternative space, but there's nothing stopping us from talking about it in the total space. So we'll give this a name. We'll call it B theta. Sorry for my passive voice. I've been editing lately. That is definitely in the passive voice. So if you ever want to see like the key indicator, it's that. Okay. But we're in the classroom. I speak like a human being. I use the passive voice all the time, except when I write. Okay. One of my grad students is writing a paper. He's very consistent. I'll tell you that. So everybody is probably me too in the early days. Sound familiar? Okay, so that's what a power function is. It's just the probability of rejecting. And here's an example of this. So if we were to complete this problem, we would need the probability, not of all of the data, although you could think of X as cap X, all of the data, but you could compress it into the minimal sufficient statistic and talk about the probability of that minimal sufficient statistic, and it would all work out to be the same. There's an easy way to do things and a hard way to do things. So if we were studying this problem right here, I first need to work out what is the probability of the min. And so you would know how to do that. You could get the density function by drawing that picture, and then you could integrate over that thing, at least potentially. In spirit, you could integrate over it. It wouldn't be too hard in this example. You'd be able to do it anyway. And then I could calibrate C to start talking about certain probabilities of rejecting maybe in the null space. So, and that's the typical procedure that people follow, is they calibrate C by saying, I'm going to put a cap on the error I make if the null hypothesis is true, and I reject, I've made a mistake. And usually they'll pick C to calibrate that mistake. And very often they'll pick 0.05 or something like that is the rejection probability. So C would be calibrated first by writing down the probability model for X1, and then I might look at the maximum in the null space that actually happens right at theta naught is where the maximum occurs. On that, you could convince yourself of that by looking at these pictures. So, and then I can pick C to relate to a probability of rejecting in the null hypothesis. Cool. So let's look at another example and just kind of outline that detail in a more familiar example. One more example. This example is in all stats books. I'm going to make this claim. I think even Stat 101 books have this example in there. So they might not have told you where it's all coming from, but this is what they teach people in high school almost. I'll say xi's are normal, theta mean, invariance sigma squared. Everything is IID. I get n data points. Okay, so I'm going to give us a hypothesis. H naught theta is less than or equal to theta naught. HA is theta is greater than theta naught. I can write down the likelihood function with this. I know I'm testing theta, which is the mean. So I already have in mind, I'll probably just jump straight into using the sufficient statistic, or the minimal sufficient statistic, since it's the lower dimensional analysis I can do. If you want to do this and think about the rejection region as the whole scatter of x's and what it looks like, you can do that and work out the rejection region in the n-dimensional space. I would prefer to condense that into something that's equivalent in a one-dimensional space if I could. So the minimal sufficient statistic for theta is what? X bar. Yeah. So everybody knows we use X bar. So let's just write down the likelihood. This is e to the minus 1/2 X bar minus theta squared over sigma squared over n. So that's my likelihood function. I would have made a huge mistake right here if I didn't know what the variance is. So I probably need to tell you that. I'm going to say this as no. So if I were doing inference on sigma and I forgot that 1 over sigma term out in front right here, I would have made this huge mistake. So I've just compressed this into the likelihood like this because I get to know sigma squared. So if you didn't know sigma squared, everything would turn into a t-test, and I would be replacing sigma squared with s squared. So, and that all comes from the same procedure we're doing. So if I did not know what sigma squared was, I could follow the exact same procedure, pretend I didn't know sigma squared, maximize over that thing, and I would end up getting back something related to s squared in the analysis, and you would end up doing the t-test versus the z-test. Okay, so this is my likelihood, so I'll draw a picture. I know where this thing bumps. It bumps at x bar. It's got some spread. I can put that in, but I'm not too interested in it. And I can start thinking about this hypothesis right here. If theta naught was over here, then the maximum in the null space, which is everything over to the left of this, the maximum would occur at x bar, which is the MLE estimate. So the maximum likelihood ratio test statistic, if theta naught is over to the right-hand side, would be 1. So the more interesting case, again, is what happens if theta naught is over here. So and then I get some maximum likelihood ratio test statistic that's not 1. So lambda x, function of all of my data, this is 1 if theta naught is greater or equal to x bar. Otherwise, this is e to the minus 1/2 x bar minus theta naught squared over sigma squared over n divided by, again, this is theta naught is less than x bar. The condition. The condition here. This would be e to the minus 1/2 x bar minus x bar squared over sigma squared over n. That's 1 right there. I guess I came in originally in this class and said, I don't really care about minimal sufficiency or anything like that. I just care about sufficiency. The data is totally sufficient. And the way I originally phrased everything is minimal sufficiency helps you out if you're computing something. You need to store less stuff in memory, and your likelihood evaluations, you need to compute less things at every step. But there's also the added benefit is that I have to make less strokes with my chalk if I'm working with a minimal sufficient statistic, which if I were taking exams, that would save me a lot of time and probably improve my score. Again, lots of ways to do things. There's an easy way and a hard way. So I'm not going to be asking you questions about weird probability models that you haven't seen before. So you should be able to recognize what the minimal sufficient statistic might be. Okay. Let's finish this up. This is exactly the same example that I was using last time. So I'm just going to look at this part right here, since that's the most interesting part. So theta naught less than x bar. Then I'm just going to have this e to the minus 1/2 x bar minus theta naught squared over sigma squared over n. And I'm going to bound this by c. So that's a number between 0 and 1. And I can just rework this thing a little bit. So I can say log c all multiplied by the minus 2. That's coming from here. And then I'm going to take a square root over the top of that thing. I do a sanity check real quick. I convince myself that thing is negative. So that's a negative. This thing is positive, no problems. So, and this is x bar minus theta naught is going to be greater or equal to that. So I flipped everything around when I multiplied by the minus 1 on both sides. And I did the exact same thing that I did last time, but I forgot this feature. So sigma over root n. That was just this. So I took the square root of that. The problem in the book has sigma as 1, the original problem, and that's why I forgot to write it down the first time. It was in cruise control. So same sort of stuff that you guys do on exams sometimes. Come here.
Absolute value.
I've got a condition on this. Yeah. So you're right, it wouldn't have hurt you to do that. So if we were doing the sharp test, the two-sided test, the point against the whole interval, we would have needed to do that. And then I would have started freaking out for other reasons. That why are you comparing a point to an interval? What the heck? So we'll go into that, not for another week or so. So this is my test statistic. I could rephrase this just in terms of x bar if I wanted to. We can write it out that way. I kind of like writing it like this. So, but it's up to you. I could define the rejection region just in terms of x bar, just by adding theta naught to each side. We'll do something similar to that in a second. So, but I like just thinking about this thing right here. So sometimes I just leave it in that form. So power function is b theta equals the probability that x bar minus theta naught over sigma over root n is going to be greater or equal to, and I'm just going to write this up here, minus 2 log c square root. But I don't like thinking about this number. I just know it's some number. So again, it's just a constant. It's some thresholding value. You pick it. So if you pick c, this is just some other number. So instead of writing it like this, which I think is a distraction, I'm just going to call this thing k. So it's just some other constant. This is a constant. So this is also a constant that relates to it. Not the same constants, but you tell me c, I could give you k. You give me k, I could give you c. So now I can think about this a little bit more, and I can start thinking about how this thing is distributed. I know how this thing is distributed at theta naught. If theta naught was the true value, then I know all about this test statistic. I know it's normally distributed. I know it's normally distributed no matter what, but I'll know exactly which parameters underlie that normal if everything came from the null hypothesis. But if things came from the alternative hypothesis, this is some shifted normal, so not centered at 0. So I can just rewrite this thing and start thinking about everything in terms of true theta. So I'm going to rewrite this, get rid of that. So I'm going to pull that over to the right-hand side, the theta naught. Again, theta naught is a constant in all of this, so I probably want to pull all my constants over here. And I'm going to rewrite this in terms of the true value of theta and give myself some options, whether or not that's the null hypothesis or the alternative hypothesis. So this is sigma over root n. This is going to be greater or equal to k. I'm going to add this theta naught over here over sigma over root n. So I've just shifted that to the right-hand side. I've subtracted off that theta as well. So I'll plug that one right here. These are equivalent to each other. I haven't changed anything. This is just algebra. So I've written everything in terms of the theta naught over on the right-hand side. So, and I'm going to be thinking about this as the truth. I don't know what the truth is, but I can still imagine that's the true value, and I can think about what this distribution is under the truth. So if theta was the true generating value for everything, then I know all about this test statistic. So if theta is the true mean, then I know that this is normally distributed with mean 0. X bar has expectation theta if theta is the true mean. So minus theta, so then that's expectations theta, and the variance in this is sigma squared over n. So that's what random variable that is. Sorry, yeah. Normal 0, 1, yeah, divided it out. So that's normal 0, 1. You can kind of imagine if theta naught was the true value, I'd plug that theta naught in right here. And that theta naught would subtract from that one, and this would be 0 right here. And I get back exactly the same thing. So under the null hypothesis, the distribution looks like that. Under any old theta, the distribution looks like this. So this would be the distribution under a presupposed truth. Under exactly the maximum of the power function in the null hypothesis, the probability distribution would be this. So I could end up just doing some sort of analysis. I can end up looking at a standard normal. So Z is typically our notation for a standard normal. And I can start thinking about this condition right here. K plus theta naught minus theta divided by sigma over root n. And this is my power function. This is a function of theta, and I can start thinking about how this varies across all thetas right here. Let's just think about this. Is theta is really, really small, what does this function do? So what does this whole thing look like? If theta is very small, I'm subtracting this off. Or let's just say, if theta is really big, if you'd like. Let's just draw a picture of this thing. B theta. So is theta's really big over here? This thing right here, this thing is getting smaller and smaller and smaller. And getting pulled away, so the chance of something being bigger than something that's getting smaller and smaller and smaller is getting bigger and bigger and bigger. So the power function looks like this. This is going to be bounded at 1. I'm going to have some theta naught in here, some value where that crosses over. I don't know what theta naught is, so I don't exactly know what this is. I don't know what X bar is, so I don't know a lot of these things. So, but I can start thinking about this. The point is that this power function in the null vicinity, so this is the null, over in that region, and the alternative region lies over here. The point being is that there's a maximum value for the probability of rejecting in the null space. and that occurs on this boundary theta naught. So that's why in Stat 101 or in high school or wherever we took this thing for the first time, we were just plugging in the theta naught and not thinking about the whole range of theta naughts. Why? Because we have the most power to detect at theta naught because this thing is increasing. So the probability of rejecting the null is the probability to detect, whether that's true or not. So, and this thing asymptotes out to 1. So what I could do is I could start thinking about this value right here, plug in the theta naught where this thing is maximized, come back around to this equation right here, and start thinking about how I want to select this value. So this is very important. So that's the max of the error in H naught. This is an important value right here, and I'm going to call it alpha. So that's typically what people will call that value as well. We'll call it the alpha level or the size of the test. It's actually the level in this case. So the naming is consistent with what they've taught us in Stat 101. So I could pick a K to do that. Let me just tell you about different types of error rates. So again, there's 2 different errors that you can make. Let's give them some names. So let's say the truth, it could either be H naught or HA. And then I can have some decision. And that could either be H naught or HA. So if the truth is H naught and I decide that theta is in the null region, then I haven't made any error. This is a correct decision. Same thing over here. So correct decisions. The error's out in here. So if the truth is H naught and I decide H alpha, I've made a type of error. I'm going to call this a type 1 error. You can tell that a statistician made that. So it's not cool at all. It just is a type of error. And this, correspondingly, is the type 2 error. And if you're from computer science or something like that, and you like to talk about precision and recall, there's a 1-to-1 correspondence between the type 1 and type 2 error and precision and recall. There's just different ways to talk about errors. They don't mean the same thing. There's a mapping between them. I have to give you N for you to do that mapping. If you don't know what that means, don't worry about it. So this has to do with sensitivity and specificity. If you've ever heard those terms, they're just recalibrations of all of this stuff. If you don't know what those terms are, don't worry about it. So they're just glossary terms, and they all kind of have something to do with each other. Okay. So I might be thinking about my maximum type 1 error and thinking about how I might make that. So the maximum type 1 error would happen right here. You can see that in the power function. So the max type 1 error occurs here. And then we give that a name as to what that error rate is. So and that's called the alpha level of the problem. Happens here, and we'll call this the alpha level. And very often what people do is they fix the alpha level. So they look at the type 1 error, they bound it so that you have a threshold on that, and then the name of the game is to control the type 2 error. There's always a balancing act between those two things. So I could end up never making a type 1 error by never rejecting my null hypothesis. I refuse to do it. I won't reject the null hypothesis. I never reject. You never have a type 1 error. What happens to your type 2 error? It explodes. So, and vice versa. You bring the other one down completely, you'll explode the other one out. So we want some balancing act on all of this. So the name of the game is to build in some artificial constraint, constrain one of them, and then potentially do something to the other one. So Neyman Pearson is all about constraining the type 1 error and then figuring out the criterion that we need for minimizing the type 2 error. I'll give you a heads up. It's the likelihood ratio test stat. That's what they proved to us. That by using the likelihood ratio test stat, you minimize the type 2 error with a fixed type 1 error. So I could end up coming up with some values right here, and I could pick K. So K, so just as some examples, I could end up coming up with alpha is equal to 0.1 or alpha is equal to 0.05. So those are the typical values I usually see. Does anybody know what these K's are? What's this one? So Dylan says 196. That's the 2-tailed one. So you need the other thing for the 1-tailed thing. 645. Yeah, you're right. 1.645. So this is the 1-tailed test. If I were doing the 2-tailed test, I'd have to recalibrate, and I'd be looking at the 2.5% error rate. So the alpha corresponding to 2.5% is 1.96 approximately. And for alpha is equal to 0.1 for an epsilon, does anybody know? I'd be astonished. I wrote it down on that piece of paper that just fell out of my pocket. I wrote it down this morning, I still can't remember. Is it 1.128 or something? 1.28 is the number. So you pick these, and it'll tell you what K is, and that's the correspondence. So that's the answer to the question, how do we pick C? We do it through this. If you wanted to know the actual value of C, you would just take K and unwind it, but nobody's ever going to ask you that. What's C, unless they're just setting up some weird test question. But that would be a step of algebra I probably wouldn't want to test you on. It's just a waste of time.
So sometimes, could there be a case where you want to minimize the probability of making an error? Like not just type 1 or type 2, but place.
Yeah, you still need a constraint in there. So there would be an infinite number of solutions.
Right.
That'd be nice. But you have to constrain yourself to what types of errors and start thinking about those two spaces. So you would have to come up maybe with a norm on how you want to balance out those two errors. So you could probably do something and say, I want the maximum of the two errors to be equal to each other or something like that in the two spaces, and then solve a problem like that. That's just not the norm. That's not what people arbitrarily chose for us. So you could do things, but you'd have to build in that constraint.
Well, what if you knew a priori, the probability that basically the prior probabilities of H naught and HA occurring?
Oh, okay.
Which of course is not
Yeah.
usually the case.
We need that lecture for next Wednesday.
That's not the
Address that
Bayesian,
question.
that's the Bayesian.
Yeah, you take the Bayesian approach. And you could start doing that, so the Bayesian might have some more flexibility, some more nods through their priors. So good thinking. So there are adaptations that are similar to this. It's just not what I'm teaching today.
Right.
But I think what you're saying makes sense, and some people do that. And I think that can make a lot more sense than just locking down the type 1 error and then minimizing the type 2. So everybody's asked this question all through statistics classes. Why do we choose one over the other? Why do we put so much importance on the type 1? And usually people say things like, well, if you're giving a drug to somebody, maybe I want to cap the probability of you dying or something like that, and then think about recovering from disease and maybe trying to maximize that. So they might threshold one of those things that is more important, that you want to just cap that error and put a maximum on it. So if you're thinking about dam failures or death or something like that, then you would treat that through the null and then cap that maximum probability. So that's the best answer I have for you. In some contexts, it makes sense to do this. In other contexts, where you're thinking about those two different decisions very equally, then you would need to do something different and maybe be amazing. Cool. So that's just an illustration of what you do with this in a very Stat 101-esque sort of way. So what we just derived is the basic hypothesis test from high school. Let's see if I want to say anything else about this. I think I do want to come back and tell you more about the trade-off in type 1 and type 2 errors. So I think I'll address the binomial problem in the book next time when we come in, where x is equal to 5 or x is equal to 3, 4, 5. So if you want to look at that example, we'll kick off next class with those examples. And basically, we're just going to define rejection regions a little bit differently, arbitrarily, show that there's some trade-off and a need to optimize that trade-off in some sense. I've already given you a full foreshadowing of how we optimize that trade-off. David and Pearson says you lock down the type 1 error rate, and then you minimize the type 2 error rate. Where were they getting that all from in the first place? They were looking at Fisher's procedure. So Fisher always said if the p-value, and that all relates to this sort of thing, so I can compute a p-value, see if it ducks alpha, it'd be exactly the same as what I've done over here. So the correspondence is 1 to 1. They were doing all of that because I think Fisher says you reject if the p-value is less than 0.05 or something like that, and they were trying to understand what they meant in trying to explain this in terms of error rates. Fisher didn't love all of that because they said you had to lock down the alpha level before anything, and Fisher, I sympathize with them, was saying things like, well, you know, p-value of 0.0499999 is very similar to a p-value of 0.05, 0.000001. And so why do you have this sharp decision right there? So maybe Fisher wanted to be a Bayesian, but he didn't realize that until he retired. So we'll never really know. But I think Naiman and Pearson, they thought they were helping Fisher, and it backfired in their face. So Fisher said, no, that's not what I'm talking about. But what they were really doing is explaining what it meant to threshold the p-values. So we'll introduce p-values in a future lecture if we're unfamiliar with them, but my guess is you've all touched on it at least once upon a time. So this locking down the alpha level and minimizing the type 2 error rate took Fisher's statement one step further. It told us how you pick the test statistic to minimize the type 2 error rate. And that's a proof we'll go through, at least start this week. I think we'll be through it by Friday. We'll probably start with the statement tomorrow and do the full proof on Friday. That's it for now, you guys. I will see you Thursday evening. I won't be here Thursday. Oh, sorry, we still have Wednesday. I'll remind you on Wednesday. It's been a long week.
Additional undertaking at the end stuff done and Friday for sure. Deal.
So maybe an office over here.
Yeah.
And maximum.
I like 5 Friday, Saturday.